All right, here we go. This is Horner, and this is section 20.6, 20.9, and 20.10 problem solution. So I have a step-down transformer. It has 4,000 turns on the primary and 200 turns on the secondary. Since it's a step-down, this should be bigger than the secondary. If the primary voltage is 2,200 volts, what is the secondary voltage amplitude? So to do this one, we know that the secondary EMF is equal to the secondary number of turns over the primary number of turns times the primary EMF. Secondary number of turns we said was 200, primary turns is 4,000, and we're going to multiply that times 2,200 volts. If you go through and do your math, you should get 110 volts. For number 32, this one's a little different. It says a step-down transformer again has a turns ratio of 1 to 100. And they want us to use an AC voltage of amplitude 170 to provide to the primary. If the primary current is 1 milliamp, what is the secondary current amplitude? So this would be the primary current over the secondary current is equal to, now remember this is an inverse of what we have here, primary voltage, secondary EMF over the primary EMF, and this is the secondary number of turns over the primary number of turns. So essentially here we've got the secondary current is equal to the primary turns over the secondary turns times the primary current. Our primary turns, remember, would be 100 because it's a step-down transformer. Secondary is only going to be 1. And then our current here is 1 times 10 to the negative third amps. So if you multiply 100 times this, you should get 0.1 amps. And that one is number 32. Let's go ahead and take a look at the next one. This one's number 34. In number 34, we have a primary coil of a transformer has 250 turns. The secondary has 1,000 turns. So this is a step up. An alternating current is sent through the primary coil. The EMF of the primary is 16 volts. What is the EMF in the secondary? So it should be bigger than that 16. So our secondary EMF is equal to the secondary turns over the primary turns times the primary EMF. Secondary turns is 1,000, primary turns is 250, and we're going to multiply that times 16 volts. So we end up with 64 volts is the EMF amplitude in the secondary. Take a looking at the next one. This one is number 42. So now we're on to solenoids. And with number 42, it says a solenoid is made of 300 turns of wire wrapped around a hollow cylinder of radius 1.2 centimeters and a length of 6 centimeters. They want to know what is the self-inductance of the solenoid. So this needs to be 0.012 meters. This should be 0.06 meters. This is our 300 turns would be capital N. And our equation here is the inductance is equal to the value for the permittivity of magnetic permittivity times the number of turns squared times pi r squared, which is going to be the area, and that's all over the length. So this would be 4 pi times 10 to the negative 7th times 300. We need to square that times pi times r, 0.012 squared, and we can divide all of that by 0.06 meters, and we'll end up with 8.5 times 10 to the negative 4th henries. And that is the inductance in our inductor. That one was number 42. Let's go ahead and take a look at number 43. It says a solenoid of length 2.8 centimeters and a diameter of 0.75 centimeters is wound with 160 turns per centimeter. When the current through the solenoid is 0.2 amps, what is the magnetic flux through one of the windings of the solenoid? So the total flux linkage here is N times the flux is equal to the inductance times the current. So the flux through one winding is going to be just the phi here itself. So phi is equal to, the flux is equal to L times I all over N, where L is mu O N squared times pi. Now they gave us diameter, so we're going to take the diameter and divide it by 2. That gives us the radius squared, so don't let that fool you, it's pretty easy, times the current. and then we need to multiply that times L times N. If I do that, I'm going to end up with 1/4 of mu O times pi times little n times d squared times I. And so now we can plug some things in. 1/4 of 4 pi times 10 to the negative 7th, and that would be a Henry per meter is the unit for that, times pi. Here we're going to go ahead and use centimeters because our centimeters are going to cross off at some point here. So we have 160 turns per centimeter, so that's 160 over a centimeter. And then we've got 10 to the second centimeters per meter. So all we're doing is getting rid of the centimeters. We're just converting this 160 per centimeter to 160 per meter is what you're doing, just making a conversion. This will be 0.0075 meters squared. So that is our diameter. And then we're going to go ahead and multiply that times our current, which is 0.2 amps. If you go through and do all that math, you should end up with 1.8 times 10 to the negative 7th. And remember, flux is measured in a unit called a Weber. And that was number 43. Let's go ahead and take a look at the next one. The next one is number 46. This one's a little bit longer, but I think it's a little bit more applicable to what a lot of you want to do. The main magnet in an MRI machine is a superconducting solenoid. It's 1.8 meters long and 25 centimeters in radius. During normal operation, the current through the windings is 100 amps and the magnetic field strength is about 1.5 Tesla. So the first thing they want us to do is how many turns does a solenoid have? So to find the number of turns, we know that the magnetic field is equal to mu O times the number of turns times the current all over the length. So we can rearrange the equation. This will make this BL all over mu I. Our B is 1.5 Tesla. We know our length is 1.8 meters. We're going to divide that by 4 pi times 10 to the negative 7th for our magnetic permeability. And then we have 100 amps. And so we have 2.1 times 10 to the 4th turns. So that's a lot of turns. For letter B, it says how much energy is stored in the magnetic field during normal operation. So here, the energy stored in the magnetic field is equal to our little UB times the voltage. We know that this value we said was B squared, so it's the magnetic field squared all over 2 times that permittivity value. And then we do pi. Volume would be pi r squared times L. Put all our numbers in. This is 1.5 Teslas squared times pi times 0.25 meters squared times 1.8 meters. And we're going to divide that by 2 times our constant, 4 pi, times 10 negative 7th. If you do all of that, you should get 320,000 joules. So that's how much energy is stored in that magnetic field during a normal MRI. So the very last question wants to know how much energy is stored if the current is only 50 amps. Since the current is 50 amps, we've reduced the current to half its original value. The energy stored should be 1/4 of its original value, so it should be about 79,000 joules. Remember, energy stored is proportional to the square of the current. So the energy stored is proportional to I squared. And that's why we have to reduce it by 1/4. That was number 46. Let's go ahead and take a look at the next one. This is number 52. And in number 52, we're looking at an inductor in a circuit. So we're looking at an LR circuit here. For this LR circuit, it says a 50 millihenry inductor and a 10 ohm resistor. So here are those two elements are connected in series to a 6-volt DC battery. They want to know what is the voltage across the resistor immediately after the switch is closed. So since the current through the inductor must change continuously, the current immediately after the switch closed is 0. So we know that the current is equal to 0. So the voltage across the resistor has to also be equal to 0 since there's no current running through it. then we can't have, if the current is 0, then the voltage has got to be 0 here also. Remember, V is equal to IR for this guy right here. And if our current is 0, then our voltage has got to be 0. For letter B, it says, what is the voltage across the resistor after the switch has been closed for a long time? So if it's been closed for a long time, we know that the current is a maximum now in here, and so all of the voltage will be running through, and so we should have 6 volts running through this resistor if it has been closed for a long time. Now they want to know what is the current in the inductor after the switch has been closed for a long time. And so for this one, we know that the entire voltage of the battery is dropped across the resistor. So whatever the current is caused by the resistor, that should be the current in our inductor. So here we're going to just say that current is equal to the EMF of the battery, all divided by the resistance. So that would be 6 volts divided by the 10 ohms, and we would get 0.6 amps. So just a kind of a tricky problem in that you don't do much with the inductor at all. We're really just thinking about kind of the concepts that happen as we have this circuit kind of get full current in that inductor. Alrighty, so that was number 52. Let's go ahead and take a look at the last one. This is number 53. Notice that we do have a parallel combination now of a 10 ohm resistor and a 7 millihenry inductor, and they are also connected in series with a 5 ohm resistor, a 6 volt DC battery, and a switch. They want to know what are the voltages across the 5 ohm resistor and the 10 ohm resistor respectively immediately after the switch is closed. So we've got to use Kirchhoff's loop rule. So notice that, remember when we have 2 loops, if I close this, the voltage in each one of these should be the same after I subtract the voltage and the voltage drop across this resistor. So to find that current, what we'll do is we're going to take 6 volts and we're going to subtract off the current in that 5 ohm resistor, and then we're going to subtract off the current times the resistance in that 10 ohm resistor, and those should be equal to 0. So here, remember, I times R is just voltage, and the sum of the voltages according to Kirchhoff's rules should be equal to 0, so that's why we're able to do this. Now we can solve for I, and I would just be 6 over 15, and that would give us a current of 0.4 amps. So let's go ahead and find the voltages across each one of the resistors. So the voltage across the 5 ohm resistor would be equal to 0.4 amps times 5 ohms, and so that would give us 2 volts. And then the voltage across the 10 ohm resistor would be 0.4 amps. Same current because the 2 resistors are in series. We're not worried about this thing in parallel. We're just worried about the current in these 2 things. So 0.4 amps times 10 ohms, and that would be equal to 4 volts. So that's immediately after the switch is closed, so we know that no current has been accumulated here, and that's why we can say the current is the same in each one of those. For number 53, part B, it says what are the voltages across the 5 ohm resistor and the 10 ohm resistor respectively after the switch has been closed for a very long time. So at this point, after the switch has been closed for a long time, the current in the inductor is no longer changing, so it acts like a short circuit. And so no current is going to flow through this 10 ohm resistor because all the current now is going through our 7 millihenry inductor. So the voltage here is equal to 0. The entire voltage of the battery then is going to be going through the 5 ohm resistor. So for the 5 ohm resistor, the voltage would be the full 6 volts, and the voltage across the 10 ohm resistor is 0 because this is essentially just short circuiting it. For the last part of this one, it says what is the current in the 7 millihenry inductor after the switch has been closed for a long time. So since the inductor acts like a short and the 10 ohm resistor is bypassed, the current through the inductor is the current that would flow through the circuit if it only had the battery and the 5 ohm resistor. And so we know that the current in that 5 ohm resistor should be equal to 6 volts all over 5 ohms, so that's just V over R. So we can actually write the equation over here, and that would be equal to 1.2 amps. So both this has 1.2 amps and this one has 1.2 amps, because remember, everything along a series circuit should have the same current. And that is the end of the last problem for this section.